Yeah, we are on time, so yeah, let's go for that. So let me explain with more detail these identifications of G mod P. G mod P, and I have this action of G on G mod P by right multiplication. Okay, and again, left and right for us is no difference. It's just a notational convenience whether we are doing things left or right, whether we are multiplying things left or right. So let me go back first to this SL2R situation. Then P is just these matrices. Well, here is a discussion whether we want A different from 0 or A positive. I want here A different from 0, not just the positive. I want the minus identity also to belong there, and then this any R. In any event, the way we will make our understanding of G mod P, I already told you that this is RP1, and let me explain why you have this identification, okay, as RP1.
Sorry, I thought that the diagonal were used positive because P equals A times N. No?
P is equal to A times 1. That's true. I don't want to add notation, and there is not universal definition of P. Actually, the P we are going to work is more than A times N, is what is called MAN, that I will discuss later. In SL2R, in SLNR, there is no much difference. It's just this 0 versus, so positive versus non-zero. So it's really very little addition we are doing here. Okay, so in this case, M is these matrices. Well, actually, it has to be in SL2, so it's plus minus identity. Okay, which then M times A times N gives you this. It's really not very important now. Okay, so let me tell you how you do this identification. And before saying that, we have this SL2R action on RP1 by permuting the lines, and this natural action here in G mod P. And the point is that this identification should be in a way that the action here and the action here are also identified. So how you do it? Well, you have R2. You have your action on R2, well, actually R2 minus 0, because 0 goes to 0, so, and it's a fully fixed point, you don't want to care about it. And then you have this vector in R2 minus 0, and actually you have the span of this vector here, which is an element in RP1. And you have the stabilizer of this guy, which is all the matrices A. Maybe I use A already for the Cartan subgroup. M, I will also use it. Oh boy. B. Okay. In SL2R, such that B of this line is this line. So E1, maybe I should have B, is this vector 1, 0. So this is a stabilizer. And then we have two properties. Property 1, and that's a property that you always have when you have an action. Actually, I should have said here. So we have also the action of G on RP1. That whenever I have this action here, the orbit of any point, let me call x naught, is isomorphic. Well, this is first the gx naught such that g in G. And I denote in general the actions when there is no confusion just as multiplying the G by the point. Sometimes there is some confusion, then I put some other decorations to try to make sure what we are talking about. And this is equivalent in a natural way, diffeomorphic, homeomorphic, depending on where are we working, with G mod the stabilizer of x naught. So this stabilizer is naturally a subgroup. The definition is essentially what is written up there, is the elements that leave this element fixed. And there is a natural bisection between this guy and this guy. And this natural bisection is, in general, a homeomorphism with whatever natural topology we want to discuss there. And we use it to identify these spaces. Okay. In this very special case, and that's what gives rise to this type of homogeneous spaces, the action is transitive. So any direction can be mapped to any other direction by a matrix. Okay, so G acting on X is said to be, and here is a standard definition, that's why I'm using it. In dynamics, we use the word transitive with a different meaning, but in actions, the word transitive is just for this, what I'm going to write now. If for every x, y in G, there exists G in G such that Gx. So you can move from wherever you want to wherever you want. Or if you use this definition, the orbit of every point is everything. Yes, thanks. Okay, so if we use this observation, this identification, plus the definition of transitive, plus the simple fact that any vector V is, well, the span of vector B is some V sub B times E1, so it's just enough to put this matrix, you put this vector V here, and the second column, you put whatever that will make this of determinant 1. Then this matrix sends the E1 to this V. This shows that the action on the RP1 is transitive, and so we get that RP1 is naturally identified with G, and here I'm quotienting to the right, but again, this is a matter of notation. Actually, it's to the left because we are acting on the left on it, but it's not so important. Modulo stabilizer, and then we compute the stabilizer of this guy, and this is the matrices that will send the direction 1, 0 into a multiple of itself. So this has to be of the form A naught. And then I have to complete to have determinant 1. So the only way of completing is allowing whatever here and putting a 1 over A here. And then A non-zero, B in R. And this is this stabilizer. Okay, so that's how we identify this G mod P. So this ends up being P. With this RP1. Now, in general, when we go to higher dimensions, we can do pretty much the same. It's simply more messy. There is much more combinatorics, so I will not give you really a theorem with the complete description, but I will give you the examples. And then the combinatorics, you can do it or you can read it. So it is an important fact, all these combinatorics, especially if you want to get deeper into all this Lie group business. This combinatorics is what leads you to classification of simple Lie groups. It has a lot to do with linking diagrams and everything. But for SL and R, everything is reasonably simple, though not trivial, so there is still things to play with. But anyway, so let's say we are in dimension n. And then I take the following space. Okay, I should first fix some dimensions. K1, K2, KL. This is less than n. Actually, for completing, I guess you take all them different. The last one you take n, the first one you get 0, even though it's silly, because the first one and the last one is not important. It's just some amount of numbers between 0 and n, and then you take the space or the set of guys, which will be B1, BL, such that the dimension of BI is KI, and BI is a subgroup of BI plus 1, BI subvector spaces. Okay, so the last one is Rn, the first one is the trivial space, and then you have, in the complete situation, you will put the 0 less than 1, less than 2, and then you are taking the point space inside the line inside the plane inside the three-dimensional space, and what is called the flag. So this is some space, which we could call GR K1 up to KL, because it's some sort of what is called Grassmannian. And we have naturally the matrices acting there. Now, at the same time, very trivial and also very non-trivial statement is that this action is transitive. Okay? So it's very non-trivial because it's really telling you something very deep. The proof is linear algebra. Is that if you know how to map several guys in a basis, then you can map it linearly, and plus the fact that bases can be completed, and on the basics, the very basics of linear algebra. But the outcome is that this action is transitive. So it tells us automatically that this guy is, and the action are naturally identified by G mod the stabilizer, and then you put your favorite flag, your favorite family of subspaces, where typically you do the natural choice. So first you put 0, then you go with canonical basis. So E1 up to EK1, the span of this. Then you do E1, EK2, and so on. So this is the most natural flag, which in the case of the complete guy, like here, what you are doing is just doing one step each. Okay? And then you have this stabilizer here, is a group, and you can check it's a subgroup of upper triangular matrices, if I wrote things correctly, with some shams, and these shams essentially are, so, well, if you want this size should be K1, this plus this K2, this plus this K3, and so on. I hope I did it correctly. In any event, it should be the same for the horizontal because it should be a square matrix here. So you can think K1, K1 plus K2, and so on. So if I didn't do things correctly, one should start counting from below. But I think I did things correctly, and we are starting from above. Okay, good. And so the largest guy, when you do this Grassmannian of 1 or what, 0, 1, 2, up to n, this is SLN R mod P, where P is, as I said, this MAN, which is this fully upper triangular matrices, which corresponds exactly to one order shams. So it's A1, A2, AN, all zeros down here, whatever you want up there. And you notice that this subgroup P is a subgroup of any of these other guys. Now, how is the action then? Well, the action you can identify in the very same geometric way as you do in RP1. You just move the flag by multiplying it by whatever linear map.
So are the Qs that we talked about last time, are they parameterized by these two poles, K1 to KL?
Yes. We are in SLNR, so yes, they are parameterized by this. There are other Qs. Okay. Wait a second. Wait, what I'm saying. No, there are no other Qs. This is all it is. Of course, you can make other choices, which in a sense amounts to making other choices of Rn, and then what means being diagonal, we will have to be with respect to these other things, and then it's a different choice of P. But yeah, that's all the Qs can be described fully in this way. When you go to other simple Lie groups, okay, the big difference is that you don't have all these guys. So not all the guys are allowed. So, for example, if you are in SP, not any family of vector spaces V1 up to BL can be mapped into any other by a symplectic map. Okay, you need some property to be respected. And so then you have to restrict your attention to the places where you are acting in the correct way. And this will give you constraints not only on the numbers, but also constraints on how are the configurations of spaces you play with. And this actually, you can go and look at all these Dinking diagrams and all this theory and see how these pop up very naturally. And this actually gives us rise to the notion of root spaces and of roots, which is pretty much related with these diagonal elements here and how they act on the corresponding upper triangular points. So I mentioned it very briefly at the beginning. We will going to study them much deeper in what is coming later in the course. Okay, so next week, maybe even before next week. But so far, let's be sure we understand this G mod Q, G mod P is very important. And it's very nice type of action because it really respects the structures. So I can cut the flags and only remember some part of the flag, and then this type of the action will be respecting these guys. And same if I start adding subspaces in between, you respect these guys as well. So it's really a very respectful guy. And you chop dimensions and still you have the corresponding embedding of SLN minus 1 inside the SLN R, and then of course it will depend on which guy you put there, but you can restrict. So this is especially important when we are going to play, like, and trying to understand how is this action of diagonal group on this guy here, and is not much different as how the diagonal is acting on RP1. Okay, so let me now go back to RP1 and see how this group G, or how the main elements of G acts on RP1. And when we go to higher dimensions, it's pretty much the same, simply you grow in dimension. There are a couple of subtleties that I will say in the case of 3 dimensions, so SL3, which is important to note. But other than that, that's what it is. So then we have this RP1, which is the circle, which I put the horizontal direction here, the vertical direction here. So these are my 2 favorite directions, horizontal and vertical. And I have this, first I have this group, e to the t1, or e to the t, e to the minus t, t in R. And then this guy has 2 fixed points, this fixed point and that fixed point. And any other element here, any other direction here, will go to the vertical or to the horizontal, like you can see from here. So this vector v goes v1, v2, is mapping to e to the t v1, e to the minus t v2. And as directions, actually, this is e to the t v1, v2. And actually, since we only care about directions, I could think of, I fix this guy being 1. And as direction, this direction is the same as this. And then this guy goes, assuming t is positive, t is negative, say, this guy goes exponentially fast to the vertical direction. If t is positive, then it will go exponentially fast to the horizontal, and then I should make the other identification and put a 1 here, the other guy below, and then I can see what is this exponentially fast convergence. And the whole point here is the fact that, so it's the circle, so I'm using, by doing this identification, I'm tacitly putting some charts next to these guys and really seeing what's going on there. Okay, so if I go to, I should, before doing that, I should do the other groups. So the other is e to the 110s. Then this guy fix the horizontal direction. So this is a fixed point, which means still the horizontal is a fixed point. But then any other direction, depending on what's the value s, it goes more the direction or start going to the other direction. So if I take the V1 guy, I multiply by 1s01, what I get is b plus s, and the second coordinate I still get a 1. So depending on whether s goes to plus infinity, this guy gets onto here. If s is negative, you start moving to the direction into here. You of course go sometimes through here, and it looks like it gets really horizontal, and it essentially gets horizontal even though the vertical component is always 1. So the ratio is going to 0. So it's really getting horizontal very much. It's not exponential speed of convergence, it's just linear speed, but still it does the show. So that's how you act here. So you have only one fixed point. Any other element just go all the way around from the horizontal to the horizontal. When you go from minus infinity to plus infinity, or from plus infinity to minus infinity. And finally, you have the rotations, which is cosine alpha, minus sine alpha, cosine alpha, alpha in 0 to pi. And then you know how they act in the lines. You take any vector, it's rotated by angle alpha. So that's what you do here. You take any guy and it moves some amount over there. And of course, there is an alpha over 2 and some pi over 2, because when I go all the way up to here, then I already have the RP1. So to parameterize RP1, I only need half of the circle, not the full circle. So which means that when I rotate, I have to be careful what angle this induces in RP2 is either 2 alpha or alpha over 2 in RP1. But anyway, so what is crucial here in general when it happens is whether this angle is rational or irrational, and this doesn't matter if you divide by 2. Okay, so that's for SL2 and RP1. So the dominant behavior is that of A, and this is due to the fact, very basic and simple, that essentially all matrices are diagonalizable over R modulo the bad ones, which are the ones which are conjugated to this complex eigenvalue or to this 1,1s. Okay? So of course, complex eigenvalue has is from an open set, so it's not that it's really so negligible, but still the really dominant game here is the diagonal matrices or diagonalizable matrices. So now what happened is in SL3. So then in SLN, it's just a little bit more combinatorial than SL3, so we don't need to care much. So it's good to play the following game. So we have this P, which are these upper triangular matrices. And then you have another, the next guy, which is Q, which is this guy. And that's it, because after Q will come everything, so you cannot do anything else. So these are the two main flag spaces, which is either you put, there is one more, but it's equivalent to this, so it's not so serious. So it's putting 0, 1, 2, 3, or you go to 0, 1, 3. You could do 0 to 3, but these two guys are essentially isomorphic. And it's using the perpendicular, if you want. Goes from lines to plane and from planes to line. And it will correspond also naturally isomorphism, putting these two zeros horizontally here. So it's not much of a difference. Okay? Now, there is a natural map on the flags from here to here, which is forget the guy in between. And this actually, which is very geometric, also has its counterpart in groups, which is just the fact that the P classes, you map them to the Q classes, and then this naturally defines a projection. Now, this guy is essentially RP2, which I could, instead of doing what I am doing, which is it's RP2 because, as I said, no, is all lines in R3. Okay, so that's what I do when I do G mod Q, is the space of all lines in R3. I could, instead of doing that, ask the entries to be positive, especially this entry to be positive, which means also to ask for P to have the 3 entries positive. And then if I ask this property, then I will have S2, which is the double cover of this guy, which is the half lines instead of the lines. So it's not really so important or serious. In any event, sometimes for me it's simpler to explain how the group acts on the sphere S2 rather than explaining how it does in RP2. But other than that, it's not so serious. It's just a matter of drawing pictures. And then the case of P, G mod P, as we saw, is essentially SO to R, 3R. And this is covering RP2. Gosh. And let me tell you that this is nothing but the Hopf fibration, modulo 2. Okay? So you can do a double cover of RP2 to get the sphere S2, and then you do the double cover of SO to get SU2, and then SU2 is the sphere S3, and this is S3 covering S2, or not covering, fibering over S2, which is the famous Hopf fibration, but this is the very same guy. And in one of these infinitely many descriptions of Hopf fibration actually goes very close to what we are doing here. It's not important for this course, it's just fun that you are playing with these guys. And when you do all these sort of fiberings of Grassmannians over other Grassmannians, well, you are also playing these all sort of fibrations of some spaces over other spaces.
For this P, you're again taking non-zero diagonal.
No, for this, okay, yes, you're right. So if I want to make the identification with SO3R, then I should take the non-zero. Yeah, if not, I have to quotient this by the permutation group. Okay. Okay, anyway, so what we care more is not so much of what is the topology of these guys, but how is the action of G on these spaces. So let's first go here over this guy, which is how you act on this RP2, which, as I said, let me think of it being a sphere directly, even though it doesn't matter. So I will do the picture as if it were R3. So you take a diagonal map. And then naturally it will preserve this plane, and this plane. So you preserve these two planes. Now each of these planes is a circle inside here. Okay, which is all directions that remain in this plane. So it's a copy of RP1 inside there. So you have these three copies of RP1, which are pairwise intersecting because this and this intersect along this point, this line, this and this along this line, this and this along this line. So you have these three circles which have these points of intersections. Now each of these three lines are fixed points for the action of this diagonal guy. And then if you take a vector inside here, it will act correspondingly. So this is the second and third coordinates. So these two coordinates will tell you what to do. And what is important, in dimension 1, we couldn't not appreciate fully because we did t minus t, and we got a 2t. So, but it was the same t. Here, the speed of convergence is, or divergence, t2 minus t3. Okay? When you look at how this load is moving towards here or towards there, it's either t2 minus t3 or t0 minus t2, depending on whether I'm moving here or moving there. And same thing when I do these two guys, I will have this t1 minus t2, and when I do these two guys, I will have this t1 minus t3 plane there. And then if I get a vector which does not belong to any of these three guys, well, depending on what are t1, t2, t3, it will probably start moving faster toward one of the planes while it moves as well toward one of the lines. So depends on how is this distribution of t1, t2, t3. So in the typical situation, we will like to move, even though eventually we could move differently, when t1 larger than t2, larger than t3, then it depends on how is t1 minus t2 versus t1 minus t3 versus t2 minus t3. These are three positive numbers, and okay, how it goes. So this plus this equals to this. So this is the larger one. Okay, so this is the fastest one. So the t1 minus t3, which tells you that this vertical direction, you are really going the fastest possible towards this. But maybe the inverse of this, so that everything is negative. But anyway, so you are going. So this is the dominating guy. Then these two guys are free to be one larger than the other or being even equal to each other. And then this will tell you whether you decide to go first towards this or first towards that, so which is really winning. But there is one more important behavior here, which is crucial, and it's why this Margulis normal subgroup theorem we state with n at least 3. And for simply groups, so this n minus 1 is what is called the rank, the real rank. And for general semi-simply groups, the assumption is this real rank to be at least 2. And the whole point is that we can assume, for instance, that t1 minus 1, let's say t2 minus t3 is 0. So t2 equals to t3, yet these are different. So it's not identity map, it's not identity matrix, but still I have this t2 minus t3 equals to 0, which means that in this t2, t3 plane or coordinate, nothing is happening. The vector is not moving there. Still, it's moving towards t1 minus t2 because this is doing, and the t1 minus t3 also is moving. but the T2 minus T3 is not moving. So vectors, in particular vectors on this plane, are not moving at all. And if I'm outside from this vector, I still will move toward this plane, but towards here, toward there, will happen nothing. So I just will move toward this direction. And this is very important because I have this movement happening, but without moving the one direction. So I have one guys which are controlled, frozen, and the rest is moving. And that's what makes the whole difference with SL2, where if I have this direction frozen, then everything is frozen and nothing is happening anymore. Okay, so that's how the diagonal, which is the most important guy. I will leave to you as an exercise how these upper triangular guys will do. Okay, you will have some quadratic type of behavior coming from this guy here, how it acts on vectors. So you still will have some planes to be preserved. I guess this plus this is preserved. And then if you do some other configurations, then it still will be preserved, but then generally you will just be moving. Okay? So this is important as well for other reasons, but not for what we are going to do. Really, the linear one is the crucial. Okay. Also good. Oh, 10 minutes, good. So then let me go back and restate something I've said. So now I have my G acting. Let me keep with this right quotient notation. So when it really comes to the middle of the proof, when we care, I probably will swap to the right quotient, but I'm very much accustomed to do this quotient to that. Okay, we have this action and we have this kernel, so I call it alpha. This is a normal subgroup of alpha, of G, because it's just naturally this alpha induces a homomorphism from this is just bisections. I don't even care they are homomorphism, it's just a group. And this is the guys which act as identity are exactly the kernels of this guy, and so this is the kernel of a group homomorphism, so it's normal. So of course I could just do the computation directly, it's as easy as saying that. So it's a normal subgroup, and we saw that there are not many normal subgroups for SLNR. Let me just emphasize that. It's a nice exercise. So let me put the statement. If G is a simply group, and N is a normal subgroup of G, then N is inside the centralizer of G. And clearly, any subgroup of centralizer is normal, and the other way around is what is telling you that you cannot do anything else. And the reason for that, this is a P, not a P. So the reason for that is, as we say, simply group automatically say that there are no connected normal subgroups. Okay, so the connected component of the identity of N will have to be trivial. this has to be trivial. Okay, so that's just by the definition I gave of simple Lie groups, which is there is no connected normal subgroup. If I do the other definition using the Lie algebra, I should work a little bit harder there. It's not so hard actually to show that still this guy is actually discrete, the n. But in any event, you take now, given n in n, take this map from G to G, from G to n, which is G you map to G and G inverse. And normality tells me that, well, this is what it is. Now, I didn't said, but I want G to be connected. So let me put G is connected. It's actually for all interesting situation, it is connected. So then you get that identity goes to n. This is connected. This is totally disconnected. Then this is identically n. And that's exactly saying that they commute. And you are done. So the same result is not true for semisimple Lie group, but what is hidden is the definition of semisimple Lie group. So, well, there are several possible definitions. One, and the nicest because it already gives you the description, is semisimple Lie group is essentially modulo some finite factors or control factors is a product of simple Lie groups. And hence you have that each factor in this product, G1 times G2. So each of these factors will be normal, and then the normal subgroups of this product will come from these factors. And then it's a little bit more painful. So that's why working with semi-simple Lie group is a little bit more complicated than working with simple, especially by that subtleties, not in the core, but all these subtleties really make a pain. Okay, so then in the last 2 minutes, let me remind you what we are trying to do here. So we have gamma, this gamma lattice. We take n is a normal subgroup now of gamma, and we try to prove that either n is a normal subgroup of G, which then it has to belong to the center by the previous lemma, or gamma mod n is finite. Okay, and by playing this alpha game there, this action of G on G mod Q, what we are going to put is put n inside the kernel of alpha, and then this will give you, okay, now is, of course, if n is G, certainly is not in the center. Then n is G or n is in the center. Okay? Okay, no, not n is G. So either n is in the center or Q is G. So either this kernel of alpha is in the center, and hence I get this, or this kernel of alpha is G, But if this kernel of alpha is G, means that this is completely trivial, and the only way this is completely trivial is that Q be equal to G. And then, what's the meaning of Q being equal to G? Well, it has to do with how I reach this step. So how did I put this n here? How I managed to do that? So this is not an obvious way. I have to manage to do this. And the way I build this alpha, so I will build very explicitly this alpha, it will give us not what we want, it will give us something else, which has to do with what is called amenability. Okay, so what I have to do now, and that's what I will do next Wednesday, is to define what are amenable groups, what does it mean to be amenable, and how these relate to this putting this normal subgroup of gamma inside the kernel of alpha for some action alpha that I have to develop. Okay, so that's it. Thanks. I told you that today we are going to start with amenability. So my idea is to try to define amenability, show the very basics of amenability, the strengths of amenability, and then try to show you how this amenability enters into our proof of normal subgroup theorem. Okay? So probably I will not spend too much time on amenability right now, so just the very basic, because it will take some time to explain how you really play this amenability into the proof of normal subgroup theorem. So anyway, let's go to the definition, amenability. So the group we are going to discuss, I'm still calling it G, but it's not SLNR, it's any group. It could be discrete, not discrete, it could be very broad situation. We are going to apply it actually to several groups in our game. So, but we want it always to be locally compact and second countable. Okay, so these are really very basic assumptions. The first assumption guarantees that we have a Haar measure. The second assumption will tell us that this Haar measure is sigma finite, because if not, it really could be even not sigma finite, and it's something manageable, so it's the Lebesgue measure you want to see. So, and only groups, all countable discrete groups are in this assumption, so it's really a very reasonable assumption. Okay, so before I go to the definition, because there are several equivalent definitions, and I want to stress essentially two definitions, maybe three. Let me introduce one more object, which is the standard action or representation of G into L to G. So when I write L to G or L2 of any group, I just mean it with the corresponding Haar measure. Okay? So unless I need to emphasize it, I will not put the measure, which I typically will call lambda G. So this action takes a function phi in L to G, and G star phi applied to a point X is phi of, and do you have two of them? And let's say I'm working with invariant Haar measure. And then I multiply to the right. So this makes this representation into a unitary representation, so it's actually unitary. So it's a homomorphism from G into unitary to G, and this we call it the standard representation, or maybe the standard right representation. We have the standard left representation, but for this we use the left invariant metric and the left invariant Haar measure, and then we multiply on the left. So and as always, left multiplication and right multiplication are mostly interchangeable. So one need to have epsilon of care. Maybe just some note here: left multiplication versus right multiplication. So if we pick lambda, left invariant Haar measure, then it means that lambda G times A is lambda A for every A measurable. But then if we multiply on the right, it can be seen, it's not really hard, it's quite straightforward, that it just multiply the measure by a fixed number that only depends on G. Okay? And this psi of G is some sort of determinant, essentially, which is a map from G to R plus with the multiplication. It's a homomorphism. Okay. Now I will give a definition and an example. G is called unimodular if chi is identically 1, so when Haar measure is both left and right invariant. And the example, there are two main examples which are important for me. One is when G is SLN R, it is unimodular. It requires some work, but it's not hard. It's quite trivial by some statement I already told you. So the big statement I told you is that G has no normal subgroups other than some trivial normal subgroups. Then the kernel of this map will be normal. And once the kernel of this map is normal, then it's either everything, so you go everything to 1, that's what you wanted, or it's the center. But if it is the center, then it means that when I quotient by the center, I get an abelian group, because this becomes an isomorphism, and we know it is not abelian even by quotienting by the center. So then the kernel has to be everything, and everything goes to 1. Now the second example, which is also very important to us, we can go further, larger dimension and make a lot of modifications of this guy, but just this is already good for me. So this is group of upper triangular matrices is not unimodular. So left multiplication is not the same as right multiplication. And even if I restrict to the case that A times B equals to 1, is also not. So it's really, these are very bad guys. For this unimodularity, well, bad or good. So actually, non-unimodular groups are very good to make a lot of computations because you will have this guy and this will let you play some game. So anyway, so that's with respect to this left versus right multiplication. So one has to be consistent, especially when it comes to these type of groups. One has to be consistent. So if it is unimodular, it doesn't matter. But if not, you have to be consistent. Okay. No, actually, yeah, my bad. I could have just left it. Okay. So we have this representation. Now, another definition. So given a unitary representation, pi from G into unitary of some fancy letter here, H, a Hilbert space, we say that P has almost invariant vectors if, okay, now I need to choose the quantifiers correctly. Okay, for every epsilon and for every subset S of G finite or compact rather than finite, yep. I have to say here, I will not stress this too much because for the situation we are going to discuss, this will be clear, but we want this pi to be continuous. Okay, so it's important that we are talking about continuous representation. What does it mean to be continuous? Well, the typical topology is what is called the strong topology, which is not the strongest topology you could put here, but it's still called the strong topology, which means that when you evaluate on vectors, things varies continuously. But again, one could consider other topologies, and it's almost the same any topology unless you choose the operator topology, then it's not really the same. There's a couple of subtleties, but it's not, for our situation, it's really not so important. So then, if for every S compact, there exists a vector V, norm of B equals to 1, and norm of pi G of B minus B less than epsilon for every G in this compact set. Okay, maybe I should have defined, but that's the obvious definition. So B naught is an invariant vector for pi if pi of B naught equals to B, pi G of B naught for every Now, yeah, let me stress something which is very important. So while in this definition now here, the vector is invariant, here there is no almost invariant vector essentially. It's the representation that has almost invariant vectors. So if I fix the epsilon and the set S, then I could say that a vector like that is an almost invariant vector for both epsilon and S. But then when I move epsilon and I move S, the vector V will have to change. So that's one observation. The second observation is that one S is a generating set. Really, the burden is in epsilon rather than in S. So once I know I have, so let's say I fix S as generating sets, and I know that for every epsilon there is such a B. Then if I take any other S, by just playing a little bit, I will be able to find also the B. So, but I'm just doing this type of statements. So that's one definition. It's important definition. Then examples is if G is compact and pi from is continuous representation, then it has invariant vectors. Okay, I will not do the details. I will just tell you what is the invariant vector. Then you will have to do the details. It's not 100% trivial, actually, the details, but the invariant vector would be the integral of and the compactness will tell me that this Haar measure is a finite measure. So this integral really makes a lot of sense. And I just need to be careful that B naught should not be 0. If B naught is 0, then it's useless for this purpose. But as soon as B naught is not 0, then I divide by the norm, and it is a full invariant vector. And if it is full invariant, then it's almost invariant for whatever epsilon you want to put. And then you are done. And this is true for every unitary representation. So that's one example. Again, the non-triviality here is one hand making sense of this integral, because this is taking values in H, so one have to make sense of H-valued integral of H-valued functions. On the other hand, you have to argue why for some B this will be non-zero. Okay, so that requires some argument, but is really not too hard. So another case, which is also very, very important, is G equals to the integers. For the reals will be the same. I'm just doing the integers. It's a little bit simpler. So, and now again, this will be with respect to any unitary representation. So I take pi from Z into unitary of H. So this is now, since the integers comes with the discrete topology and is generated by an element, this corresponds to a unitary map A from H to H. So that's what it is. Oops. So U of n is nothing but A to the n. So that's what it is. And then the theorem is essentially given by von Neumann Okay, von Neumann theorem, which is previous to Birkhoff ergodic theorem, but is the L2 ergodic theorem, actually is true for H, and it can be deduced from several fixed point theorems, or there are a lot of ways of saying it, but essentially the point is that if you take B sub n equals to sum from I equals to, well, one can make different choices. Let me do even the more standard choice, 0 to n minus 1 of A to the I of B. Then you are given S, you are given epsilon, then you will make a choice of n large enough so that this guy is an invariant vector. Okay? An almost invariant vector. Again, you will have to normalize, divide by the norm of this guy to make sure this is norm 1. Or differently, I can modify the definition here, and now I don't need to normalize. I just need B to be non-zero. Then I don't need to divide by the norm. Okay. Okay. So this is very important, and the same is for R. In the case of R, then you still have some generator, but then it's an infinitesimal generator. I don't want to enter into infinitesimal generator, but still you do integral between 0 and t of pi t of b dt 1 over t, and you use this guy for that matter. Okay. Good. Now the definition is G is amenable if the standard representation has an invariant, has almost invariant vector. Okay, so and let me make the following observation. When I have this G equals to the integers, then the L2 of C is the same as the little L2 of C, and the standard representation does not have an invariant vector. So it has almost invariant vectors, but not invariant vector. Actually, the following lemma is very simple. I think it's beautiful, but it's really very simple. It says that if the standard representation has an invariant vector, a non-zero invariant vector, of course the 0 is always invariant. And here I should say does not have a non-zero invariant vector, then G is compact. Okay, so the only groups which has invariant vectors for the standard representations are the compact groups, no one else. And for the standard representation, it's very easy to see that what is the compact, a constant vector. Well, you want phi of gx, I'm doing left invariant, but it really doesn't matter, to be this for every g. Okay, so that's been left invariant. Now, of course, there is an almost everywhere discussion here, but let's not care about the almost everywhere discussion. So, if you want this to happen for every g and for almost every x, then it means that this function is constant. Okay, so it has to have the same value as the identity. So phi of g is equal to phi of the identity. If I were able to evaluate it at the identity, I cannot evaluate at the identity, but I can do some argument and show that phi is constant almost everywhere. Now, if phi is constant almost everywhere, it means that the constant function is an invariant vector, but this means that the constant function is in L2. So it means that the measure of the group is finite. So it means that the Haar measure of the total group is finite, and then you can see that if the measure of the group is finite, then the group has to be compact. This requires some work, but it's not so hard. Actually, the simplest way of arguing there, I think, is just using the definition of compactness, the standard one. Take a covering of the group and use this finite measure of the total group to find a finite subcovering. So that pretty much should be. I'm sure there are other ways, maybe even simpler ways of characterizing, since after all, it is a group. Okay. So which means that, on one hand, compact groups are amenable because the constant function is invariant. That's even simpler than, well, in this case, we're about general unitary representation, but anyway. The integers is amenable, the reals is an amenable group. Now let me put the next lemma that enlarge quite a bit our set of amenable groups. One, if G is amenable and H is closed, then H is amenable. So the closeness here is very important. So it's not just being a subgroup, because being amenable is not an algebraic property, is a property of topological groups, because we are talking about representations that are continuous. Okay, so if the group is not closed, this may fail. Okay, product of amenable of, okay.
Formulate it in the context of short exact sequence. Like the middle term is.
Yeah, but I wanted to do, yes, that's true, but I wanted to do countable product. Maybe it's better to do what you said. Then I have finite products at once. Okay, so if I have the following sequence, okay, it's of again locally compact and countable groups where these guys are continuous guys and everything is closed and whatever it has to be. So different way of writing it is n is normal in G, n is closed, H is G mod n, so this is a different notation for this business. Then if n is amenable and H is amenable, then G is amenable. Okay, so if these two guys are amenable, then this guy is amenable, which implies that product of amenable groups is amenable. But it's more important than just products. Still, let me put one before I continue discussing this more important than products. 3 is if G is amenable and closed, then G mod n is amenable. So I need the closeness of n, because if n is not closed, then the quotient, the topology of the quotient is a disaster. I do in R mod Q. So the topology of R mod Q is really a disaster. We don't want to talk about this guy. And yeah, also, I don't think it really needed in the definition, but I hate when groups are not Hausdorff. So everything here is Hausdorff. Okay? So the closeness in particular, you will need it for the Hausdorffness of this quotient. Okay, a corollary of this, plus several other very important and basic theorems of algebra, is that amenable group, abelian groups are amenable. So this comes from classification of abelian groups, which is a very non-trivial subject. It's all Pontrjagin theory goes into it. It's a beautiful thing. Let's assume life is nice already, and so we don't need to care about it. Especially, so all this Pontrjagin theory is especially important for locally compact second countable Hausdorff groups. So really is for the type of guys we are caring, and this will tell you that they are inverse limits of reals and integers and finite groups. So you have all the p-adics, you have the solenoids, you have the vector spaces, pretty much. This is all. So abelian groups are amenable, and solvable groups are amenable. And the reason for that is that the solvable group, by the definition of solvable, is that you have this sequence Gi, and that's the definition of being solvable. And at each step, you will have Gi quotient by Gi plus 1. This is amenable, and the Gi plus 1 is amenable by induction. You start from Gn minus 1, which is abelian because the commutator is 0. So abelian is amenable. The quotient is abelian, so it is amenable, and then property 2 tells you that then the Gi is amenable. And then you go back all the way up to G naught equals to G. So that's how you get that solvable groups are amenable. Let me just remind you the definition of nilpotently group, which is very similar to solvable. The main difference is good. So in the case of nilpotent, you still have n not being equals to n. N1 is n times n, but then ni plus 1 is n times ni. Okay? And of course, you want n sub n to be 0. So you want it to finish. So while here you are just putting the commutator with itself all the time, here you are always comparing with the total. Okay, and the main example of solvable is our beautiful P, which I apologize that I keep on using P for two different things. Sometimes I use it for A times n, sometimes I use it for some sort of compact extension of A times n. But anyway, let me keep on doing that. So this is this group is solvable, but it's not nilpotent, and n is nilpotent. So this is solvable, not nilpotent. And then we have this with ones in the diagonal. This is nilpotent. Okay, and actually, it's sort of magic, but it's always true in the setting of simply groups with this sort of definition of P, A times n, is that P times P equals to n. So when you do the first commutator of this solvable, give you nilpotent already. And then once you know this is nilpotent, then certainly you will be finishing infinite steps. This is, for most nice solvable groups, so all of them coming from matrices essentially, this is always true. The first commutator goes to nilpotent. Now for general solvable, I'm sure it's not true, but I have no clue. My algebra is not so strong to discuss it. Okay, so we have this notion of amenability, which so far has no use. We have a lot of examples of amenable groups, but we never care much about this, how to use this amenability. Now, amenability, the French name is moyenable or something like that, and actually, in a sense, the best word would be averagable, so which is place where you can take averages even if you cannot really take the average. So that's the point of an amenable group. And the best example of what's the usefulness of being amenable is what I erased here. So let me write it again. So an amenable group allows you to do something like what I'm writing here. Do some average of iterates of vectors. Okay? So there is an equivalent definition, which is exactly to the point of this. Okay, I think that's how you write Follner, which is the fact that G is amenable if and only if for every S G compact and epsilon positive. Again, as before, you could take S a compact generating set and forget about the S. Okay, what is important here is the epsilon. there exists a subset A in G, measurable, such that lambda of A, symmetric difference A times G is, okay, let's keep on using left-right notation. For every G in S.
Sorry, it says A minus EA.
This is symmetric difference. I'm really trying to remember if I want the lambda of A being here. I think I do want. It's not so important in general.
You just rewrote the definition. The former lemma should be more like a sequence of sets.
Yeah, but this is because you remove the epsilon if you do the sequence of set. So the sequence you produce by taking epsilon 1 over n, and then, or maybe better than 1 over n, that's why you can start playing with the lambda of A in a better way. So, yeah, I think it's, yeah, the lambda of A is good. Oops, my bad, sorry. Good. So, yeah, the example, you just will take A as being minus n actually for one very big n, and then S amounts to translations. So, and as I said, you only care about S being a generating set. So let's say you take S being 1 and minus 1 just to generate as a semigroup to make things really nice. And then when you are doing A plus 1 or A minus 1, when you do symmetric difference with A, you are just forgetting the n, the minus n probably, and adding the n plus 1. And here this guy also will have 2 points, and then really you are very small with respect to the total guy. Yeah, and as I said, yeah, certainly you need the lambda of A there. If not, it doesn't make sense. Sure. Okay. Okay, and it's this property actually that allows you to define what is a Follner sequence. So a Follner sequence will be a sequence A sub n, where you take epsilon to be 1 over n or 2 to the minus n, whatever, something which is fast convergent, and then it's a family of disks or whatever of sets. It could be very ugly sets after all. So that when you translate these sets from the measure perspective, they are not moving too much. Okay? Like this type of sets. And then when you have something like this, your averaging method would be you take these guys, and these will produce an almost invariant vector. Okay, so you have the epsilon and s from the definition of almost invariant vector, you go and look essentially by the same epsilon and s here, maybe some very slight modification, and that way you produce an almost invariant vector. Now, being able to do these averages is what allows us to define, to give a second definition of of this that I will do really to the point we care. So there is a more abstract definition, but I really want a more dynamical one, so I really will state the dynamical guy, who says that G is amenable if and only if for every action by homeomorphisms X compact and metric again continuous there exists mu, the probability measure for on X invariant by alpha of G for every G. Okay, in the case that the group is the integers, this is essentially the famous Krylov-Bogoliubov Theorem that says that any homeomorphism of a metric space leaves invariant a probability measure. Same statement for flows is amenability of R, and the fact that this follows for other abelian groups or for solvable groups is just this lemma. And the proof is the standard Krylov-Bogoliubov, and is due to this. You call this mu sub A, send epsilon to 0, S, as I said, is a generating set. You fix it once and for all, and this A epsilon, take this mu A epsilon, take a subsequence, going to some limit, and this will be an invariant measure. You have to check, but the definition is just to make this true. Now, the proof of Follner, as I said, is pretty much the definition of being almost of the existence of almost invariant vectors. So you play a little bit and you really get over it. There is a second version of this statement, which is a little bit more abstract, that we also will need it later. And it is, instead of putting here omeo of X and an action of G on this compact metric space, you look at a representation of G on affine maps of a compact convex space, which for this matter would be the induced representation of G on the probability measures on X. So this set of probability measures is a compact convex space, and this alpha induces a representation by affine maps there. Now, the equivalent statement is, and I think I will not be able to talk about anything else, so it's better I finish with this other statement. So this other statement says following: G is amenable if and only if, whenever rho K compact convex set, and when I say compact convex, I'm assuming K is inside some vector space with some topological vector space, and the induced topology makes it compact. And again, assume all countabilities and everything so that this is really compact metric space. Just don't make it a problem. I'm having in mind the probability set of probability measures. And affine match on this convex set is whatever is an affine map on a convex set. So it's restriction of affine map on the total space. So I have this representation. This is a group by composition. So this is a homomorphism. Then there exists nu in K such that rho G of nu, so it has a fixed point for every G. Okay, and the proof is again the same. Instead of putting this delta x naught, you just put mu or nu naught. So you take and taking subsequence, this will go to your decide guy. So, okay. Yeah, maybe let me go 3 more minutes over. So the next is also very, very important. One free group on K elements, K at least 2, because on one element is the integers, is not amenable. This is rather easy to show. You just need to make an action of the free group on a compact metric space, which will have no invariant measure. And the simpler way will be just take the circle, take a homeo of the circle which has only one fixed point. Okay, the one as we saw it, which goes all people go all around, it has this only fixed point. That's F. Then take G, that simply move this fixed point. Okay? G rotates it. So it's rotation by alpha, or anything that doesn't fix this point. Then, since it's free generator, free group on 2 elements, once I specify F and G, and I specify an action, and this action cannot have an invariant measure, because if it were invariant measure, we have to be invariant by F, so it has to be delta. But this invariant measure is not invariant by G, so there is no invariant measure. So this tells you that this free group on K elements is not amenable. More important for us, SLN R is not amenable. And the reason why it's not amenable is pretty much same as this. Let me do the SL2 because it's simpler to draw the picture. So we have the circle again. So if it is amenable, there is an invariant measure. Okay, so now the circle is RP1. We know that SL2R acts in RP1, and we know that this matrix has, like this example F has this fixed point and no other fixed point. So if it were amenable, there should be an invariant measure, and the invariant measure should be then this fixed point. Then I take a rotation cosine alpha minus sine alpha cosine alpha, this rotation will rotate this fixed point, so it will kill this invariant measure. So there is no way this measure is invariant by this other guy. So there is no invariant measure. So this is same thing you do in SLNR, but then with the corresponding spheres and pretty much the same game. It's a very important example. It's very simple. It seems naive and really there is no richness here. It is extremely important. So all this theory we are discussing here has behind the fact that the non-amenability of SLNR thought as the lack of having an invariant measure for an action comes exactly from here. So there is, if you take an action and this action does not have an invariant measure, it's because there is in some place hidden there inside your action or outside your action but related to your action a picture like this sphere here and this projective action on this sphere. And we are going to explore it and try to find this guy right now. Well, not right now, next Friday.
So in our case, it should be the SL action on the G mod P.
Exactly, exactly. And actually, it will be at the end of the day the G mod Q.
Okay.
We are going to find, so that's how this G mod Q will appear. Okay, so, but this we will discuss carefully on Friday. Okay, thanks. Okay, so last Wednesday, we spent quite a bit on amenability. Now is the day to show some amenability of some guy. So let me remind you what is our goal. We have G in SLNR, gamma is a lattice, N is a normal subgroup of gamma, and we want to show either gamma mod n finite or n a subgroup of the center of G, which is hence finite. And actually what we are going to show is that this guy here is, so this is normal subgroup, so this is a group. And we are going to show first that this group is amenable. So that's why we wanted the notion of amenability. So we will show that gamma mod n is amenable. And this will be half of the problem, because the other half actually is not that it's much simpler, but still we will treat it simpler, which is about what is called property T. And once we put amenability with property T together, we get that the group is compact on finite, in this case of discrete. So this will give this is finite. So, but of course I shouldn't put a dot here. So we will show that this is amenable unless something happens, and something happens is n is a subgroup of the center of G. Okay, so now that we have this, how we show that this is amenable? So to show that gamma mod n is amenable, we take some action from gamma mod n into some x compact metric, and we need to find an invariant measure. To find an invariant probability measure. Okay, for us. So if we can do this for any action, no matter what is the compact metric space, then we are done. Okay? So we need to find this invariant probability measure. Now, let me remind you that we have this action on x now, and this induces an action that we still call by alpha on x of the lattice on x, which is trivial on n. So alpha of gamma is identity for every gamma in the normal subgroup. Okay? So now we have the action of this lattice gamma on this compact metric space, which is trivial on n. Now remember what I told you when we discussed amenability, especially amenability of P, G, and all these groups, SL and R, is that the non-existence of invariant measure here for some action of gamma on x will be due to some guy G mod Q happening in some way related to this action. Okay? So so if I manage to do it really in a very coherent way, in such a way that I found now this action and n still acts trivially, then you see what I get. I get that the only way n can act trivially on this G mod Q is either n is inside the center, that's what I want, or Q equals to G. But if Q equals to G, this action is trivial, and this will produce the invariant measure. Okay? But I need to make much more specific and clear how is this relation between existence of invariant measure for this guy and this gamma acting on G mod Q. And that's what we are going to do next, is how to build this gamma acting on G mod Q from this gamma acting on X. So this comes from a construction due to Furstenberg, a very clever construction. And then I have to state Margulis Factor Theorem, which is a very important, is the key to the proof, which is how Margulis proved it actually, the original theorem. Okay, so Furstenberg construction. So I have this action of gamma is a lattice in G, into X. So the first thing is to do what is called the suspension. It has some other names, which is induced action. I like to call it suspension. It's more dynamical point of view. So let me remind you, for the ones that have seen dynamical system course. So when I have a map from a space to a space, I can embed this map into a flow in such a way that F is the Poincare return map to some section which is naturally identified by M. And the way you do it is by taking the space M times R quotient by some relation. You call this MF. And the relation is X T. You relate it with X. Okay. Actually, just to be coherent with what I'm doing here, it's better to do R times M. And then is Tx is related with T plus 1 F minus 1 of X. And why put F minus 1 is some sort of coherent. You can do things slightly different. That's one convention. Make it easy. But everything goes the way you want. And then you have naturally a flow. So R acting on MF by Ft of the pair, or Fs of Tx is just T plus S is this equivalent class. And so you do nothing in the second coordinate in the way you write it, but the equivalence relation is telling me that something is going to happen when I go further than 1. Okay, so here is times 0 times 1. I start from here. I just move horizontally. And when I reach, so here I was in the point 0x. When I reach the point 1x, this is the same as the point 0f of x. So I come to the point f of x. And if I continue all the way to the point 2x, well, it corresponds to the point f2 of x, and so on. Okay, so that's a suspension for an f. And actually, the same thing happens for any group action. Okay, and even you can go further. But what is important here to do this suspension is the fact that C here is a lattice in R. Okay, so well, here I make this relation. One should complete it to make it transitive. Okay, so if you want to complete it to make it transitive, what you would do is put T plus N and F minus N of X. And now is a complete description of the guy. And okay, as said, what was important here is that C is a lattice in R. That's what really allows me to make all this construction. So the lattice, the discreteness property, is what makes this quotient space a Hausdorff space and some nice geometry similar to M times R. So it's locally homeomorphic to M times R. And that's the discreteness. Now the fact that the R mod Z is compact is what will give me the compactness of this MF. In the more general situation, as we are going to do now, G mod gamma may not be compact, but will have some finite volume. And then this space still will have some sort of finite volume like business. So we define G times X under the relation where Gx is related to G gamma alpha of gamma inverse applied to X. So that's the relation. We call this space M alpha, X alpha. In case gamma is co-compact, sometimes just abuse of notation, we do this, or sometimes we do that. There's several notations for the very same business. And in case gamma is co-compact in G, we have that this space, assuming X is compact, this space is compact. In case gamma is not co-compact, then this space is whatever it is. But the same as in the reals, you have a natural projection. This is true for any lattice in any group. And actually, only discreteness, so any subgroup. After all, from the purely construction, you just need gamma to be a subgroup of G. And actually, you can do some more general construction where you don't even need gamma to be a subgroup of G. You just need gamma to act on G and on X. But let's not enter into that. So you have this natural projection from X alpha into G mod gamma. Okay, let's call it pi instead of p, because p will be a lot of guys. So we have this projection pi. And yeah, it's just projection into the first coordinate. Gx maps to G times gamma. So it's a natural map. So it's well defined. Projection into the x coordinate is not well defined. Still, we will have to play at some point with projection into this other coordinate. But for this, we will have to go and play with fundamental domains or things like that. But we have the pre-image of some element in here, which we sometimes denote it by mg gamma, which is a fiber of this fibration here. Okay. So this is a fibered system. We have a G action on X alpha, and you take G, you take, let's call it A, times Gx is nothing like very similar to there, but here left and right is very important because it's not abelian, so it's A times G times X. So that's how you have to act. You cannot multiply from the right because it's gamma who is multiplying on the right, so you multiply it from the left. And this, you can see that this is well defined, same way it was well defined before, and this defines an action of G on X alpha. And as before, if you take this fiber and you think of the return to this fiber, then what you are getting over this fiber is the action of gamma on this fiber. Okay, so if I do gamma star E times X, what I get is, well, maybe it's not exactly what I wanted, but it's close enough to what I wanted. This is gamma X by definition, and this is the same as E alpha of gamma inverse X. Okay, so I have the E inverse action, but that's pretty much the same idea. Okay. Now, why I'm doing this construction? So there is a very basic reason and reasonable reason, which is stronger than why I do it here for the real. And the reason is the integers is a very well understood guy. But gamma is not. So I have no clue really who is gamma. So the whole business here is to understand what are the lattices. On the other hand, G is SLNR, and SLNR is pretty well understood. So I really understand very well a huge amount of the subgroups of G, but not the ones of gamma. So when I come to a gamma action, to a G action, I have better hope to understand what are the actions of G on X alpha and how to produce an invariant measure for the G action instead of for the gamma action. And then it will be not hard to show that if I build an invariant measure for this action, then I will be producing an invariant measure for the gamma action. And then instead of trying to show that this guy has an invariant measure, I will show that this guy has an invariant measure. No, so well, there is a lot of information, but no, they are far from known.
So we have SLNZ.
You have SLNZ?
What's the next example?
This is not easy at all. So there are plenty of compact lattices. Well, I'm saying plenty. So it's so Margulis, if you want, give you some sort of construction. So that's Margulis super rigidity. And actually, more than just super rigidity, the arithmeticity, I don't think we will reach the arithmeticity statement. But Margulis proved that all lattices in SLNC are arithmetic. So he proved that, well, in the case of SLNR, what I'm going to write is essentially true. So actually, not to make mess. So PSLNR is you just quotient by this plus minus 1 subgroup, so that the center is really trivial. So in the odd dimension, you don't need to do anything. In the even dimension, you quotient by this guy, and then you embed in some way this in SLNR, or even PSLNR for that matter, for some big N. Okay, so it's some embedding rho, which is a representation. That's what is a representation of. Okay, now you want this rho to be defined over the rationals. Okay, so this is naturally identified as a subset of R to the N. This is naturally identified as a subset of R to the N. Side, and then you can show, is again not too hard because these representations are all classified by ancient theory, so you have to go to your Lie group course, that these are polynomial. In these are n variables to these are capital N variables. Now you want the coefficients of this polynomial to be rational. So I want this representation to be like that. Yeah. I forgot the square. Sure, thanks. So I want this to be, to these coefficients of this representation to be rational numbers. And once I have this, then I can pull back SL and Z from there, or PSL and Z from there if you want. And you can see that this, let's call it gamma rho, that this is a lattice. So this requires some effort, but is not impossible. So we need to assume that rho is injective, which is not a strong assumption. I will comment on it in a second. And this gives you a way of building lattices. Give any representation the way I told you, being injective, so 1 to 1. And okay, let me discuss the 1 to 1 property. So is rho 1 to 1 or not? So who decides that? The kernel. Now the kernel of rho is a normal subgroup of SLNR or PSLNR. So it's either trivial or everything. So which means that this representation is either trivial or is injective. So just don't take the trivial representation, take any other one, will be injective by definition. Assume it's defined over the rationals. This way you build the lattice. Okay, so now what is Margulis Arithmeticity Theorem? Says that if gamma is a lattice, then there exists rho from SLNR into SLNR defined over the rationals such that, well, on some gamma hat, which is a subgroup of gamma, or well, even better, such that gamma intersected gamma rho is both finite index in gamma and in gamma rho. Okay, so this is called, so this fact that I wrote here on the at the end is called commensurability. So it's saying that gamma and gamma rho are commensurable, and this is because they are almost the same guy, so up to some finite index business. So these are all the lattices. That's what Margulis arithmeticity is telling you. So that the gamma rhos and some guys which are more or less the same as the gamma rho up to some finite index are all possible lattices of SLNR. Now, in a sense, this tells us that we know a lot about the lattices. Okay, it's pulling back SL and Z in a sense. But there are two caveats, so it's not so trivial to understand how these guys are really playing the game. And secondly, to prove this arithmeticity, you will be proving, I think historically, arithmeticity is probably before the normal subgroup theorem, but it's the very same line of work. So he proved all these theorems in less than 10 years, and he was playing with all the concepts. So okay. Okay, so where were we? So do we have this digression about lattices in SLNR? I don't think we will be able to cover this. Well, arithmeticity, almost sure no, because it really will require to not only to prove super rigidity, which we may discuss it at least. Hopefully we could even prove it, but even if we do it, you really need to go and prove it over p-adics, which is not so much hard, but it's a pain because you have to take into account several things and be careful with several other things. And then discuss the number theory, which is fun. It's really fun, the number theoretic part. And, well, to eventually deduce this business. Okay, let's go back to our discussion. So we have this G action on X alpha. Yeah, I will write it again now, so don't worry. So actually, let me bring this back down. So we don't need to do anything here. So I have this induced action G on X alpha, and we want to find an invariant measure for this guy. Okay? And we will try to do the same thing we do for a diffeomorphism or for a homeomorphism or even for a flow. Okay? So you start a guy, you take any measure and you start averaging it. Okay, so that's the standard proof for a flow or a diffeom. Now, but remember that G is not amenable because G is SLNR and G is not amenable. So we will not be able to average on G. So then we still will try our best. Okay. Okay, so what does it mean to we try our best? It means that we take P, which for us now is MAN. N is upper triangular. Once in diagonal. A is diagonal. And M is the centralizer of A in G. So these are the G's in G such that GA for every A. Okay, and remember G is KAN and this is SO.
So for this A, the diagonals are positive.
Yes, for this A, diagonals are positive. Yes, positive matrix. Now this M is essentially permutations. Permutation matrices with plus minus ones. Wait, no. No permutation. It's the plus minus one matrices. Oh, reflections, yes. No permutation. Yes, exactly. It's all possible combinations of plus and minus one. This is M. So I'm writing this way because whenever you have a simple Lie group, so this extends to simple Lie groups, whatever I'm saying, and then what you will care is the fact that the simple Lie group have this decomposition KAN, the P will be called MAN, and this definition of M, A is Cartan subgroup, N is the N is N, whatever it is. It's the space of roots corresponding to whoever, doesn't matter. Okay, now A times N is solvable because actually A times N bracket A times N gives you the N, and N is nilpotent, and M is compact. It's finite in particular, yeah. So since you have this finite extension of solvable, we still get amenable. So P is amenable. Which means that I can average on P. So, corollary of all our discussions, there is mu an invariant measure, an invariant, okay, a probability measure on X alpha invariant by P. Alpha of P for every P in P. And here, remember that we are still calling this induced action, we are still calling it alpha. Okay? So, okay, we don't have a G-invariant measure. We were looking for a G-invariant measure. We are not going to succeed, actually. Because if we succeed, we are proving that in all cases gamma mod n is amenable, and we are doomed to fail. So at some point we are going to fail, and gamma mod n will not be amenable. But in this case, n will be part of the center of G. Okay? So, but we have to fail here at some point. Still, for P, we get this invariant measure. I would like to have it ergodic. I will say epsilon about ergodicity in a second. It's not really an important condition. So it's needed, but it's not really the the most important thing here in this construction. But yeah, maybe just definition, mu is ergodic if and only if the only invariant set has measure P-invariant sets has measure 1 or 0. Okay? And the ergodic decomposition theorem will allow me, I will not go through that, this is standard dynamical system, you can just look at the ergodic decomposition theorem, will allow me to add the word ergodic here. So this measure mu that exists, then you do some ergodic decomposition and it will be ergodic. It's not really very hard. I maybe mention it again in the construction that comes next, because it says, I'm not sure to call it a different proof of the ergodic decomposition theorem, because at the end of the day, probably it's the very same proof as always. But as a corollary of what we are going to do, you also will have this ergodic decomposition. Okay, so I have this P-invariant measure. Good, that was something. Since I'm trying to build a G-invariant measure, I have this P-invariant measure. Now I will define a special guy, Q, which it will be useful. It will appear again with other definitions, this Q, but it will always be, at the end of the day, the very same Q, even though it may appear in different ways. I will define it. So let Q be all the G in G such that alpha of G star mu equals to mu. I could define Q mu, but since mu will never change, well, maybe later will change, but not yet, that's just Q. So it's the group, the subgroup of G that leaves this measure invariant. And then the properties I have, naturally by definition, is that P is a subgroup of Q. And second thing, which is not hard, actually, maybe I should have stated this first. Q is a subgroup, but it's not only a subgroup, it's a closed subgroup. And this is simply because everything varies continuously on G. So Q is a closed subgroup of G, which has P as a subgroup. Very good. So I wish Q were G. If I prove that Q is G, then I will be able to show that the original alpha had an invariant measure. So this is the Q that we were talking about in this G mod Q. Okay, but we will need to make this construction and explain how really everything goes, because at the end of the day, N will have to act trivially on this G mod Q. And so I really need to make the relation careful.
Q can be equal to P as well.
Q could be equal to P. And I have to say, I would say that most likely it will be equal to P in all situations. So there is really no reason you will be better than P, even though, well, there are cases where you're better than P. But yes. Yes. So amenability will guarantee you P. There is nothing in the world that will guarantee you more than P. Okay. So this is first part of Fürstenberg construction, is to have this invariant measure. Now I need to do some disintegration. Which is a measure theoretic version of conditional expectation. Okay, so conditional expectation is more probability, this is more measure theoretic and more graphic. So remember, we have this fibration, and so I have a measure on this ambient space. Now the first lemma, which we will be proving later, says that P star mu is lambda. I don't really need it now to know it, that is lambda, so P star mu will be some measure here, okay? And for the time being, that's all I need, but I later will need to know that this is actually Haar measure on G mod gamma. Okay, and actually, this follows from the following theorem, which is very important. Probably we will prove it later. It's not really. Extremely hard is beautiful, which says that Haar measure, so lambda, is the unique P-invariant measure on G mod gamma. Okay, so that's really a beautiful statement. As I said, it's not really impossible to prove it, but we don't need it. So certainly the theorem implies the lemma, and actually the only way, the way we were arguing here to prove the lemma is proving the theorem. I could argue otherwise and build the measure mu in a way that it projects to lambda directly. So I could have done this. Doesn't really matter. So by now, what the only thing I care is that this measure projects to some measure, probability measure down here, which is called lambda, and it happens to be Haar measure, which will be useful later, not now. Okay, now this is about the projected measure. Now there is what is called the fiber measures. So you can disintegrate this measure. So if I do here a scheme where the base is G mod gamma, and then I have all these fibers being copies of X, then I have a family of measures on these fibers, a measurable family of measures on these fibers, so that the total measure can be written as some double integral. Okay, so let me write this proposition by Rocklin. So this up there. Rocklin decomposition of this integration theorem. Actually, Rocklin, even though in dynamics is very much known for this theorem, which is actually an exercise, as I said, is definition of conditional expectation, is non-trivial. You have to play a lot with measure theory, but typical work with measure theory. He's much better known mathematically for his algebraic topology theorems, so especially for four-dimensional manifold topology and characteristic classics and blah, 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 which later gave rise to a couple of Fields medals on this matter. So not for him, he was old enough, but anyway. So it's the same Rocklin. Not the same with Egorov or other of these Russians. So there are several Egorovs. So I made the mistake of thinking that the same Egorov did everything. And no, so there is some Egorov doing some measure theory, some other Egorov doing other theory, but no, with Rocklin is the very same Rocklin doing everything. Okay, so Rocklin disintegration, I will just state it in the setting we are using it here, is very much general. So it says the following: there exists a measurable map let's call it phi from G mod gamma into probability measures of X. So here I'm identifying this X here with the fiber, which is X sub G mod gamma. But anyway, so that for every function u from G mod gamma, from X alpha, I'm sorry, and here I said measurable means Borel measurable. Okay? So this is naturally a compact metric space, and this has its topology, and this is Borel measurability. So pre-image of compact set or open set here are Borel measurable. So that for any in L1 mu, say, the integral of u of gx d mu is the same, this one x alpha, is the same as the double integral of u of gx d phi g of x. Yeah, maybe let me use this notation. Phi of g is equals to mu sub g. So then this is mu sub g of x d lambda of g. And this is happening over x, and this is happening over g mod gamma. Okay, so this measured phi g, I call it mu g. And I think it's even formally correct what I wrote, but in any event, even if it is formally correct now, I will eventually do the abuse of notation that the space X and the fiber over the point here. I'm just using the same letters and the same measure. Okay? Okay, so so this is Rocklin disintegration, which gives me this phi from G mod gamma into P of X. So it's a family of measures. So let me remind here. Into P of X. Probability measures on X. And okay, what I wrote before is about any measure. So as soon as lambda is the projected measure, this is true for every measure. Okay, so that's the disintegration. Now I'm disintegrating not any measure, I'm disintegrating this measure which is P-invariant. So this implies that phi of P times G gamma is the same as phi, oops, not of G, but of G gamma for every P. Okay? And I should add here almost every G gamma. Okay, so this phi function has this P invariance. Very good. Now I will still call it phi, and I will extend naturally this function to a function from G into P of X. Just take a point G, project it, and do what you have to do. And now comes one thing that I really would like you to be careful and do it by yourself, which is write down very careful this integration there, taking into account this identification of X with the fibers. Okay? And then do the next step very carefully. Okay? So it's a very nice exercise. It's good that you do it by yourself. I could do it here in the blackboard, but it's better that if you do it by yourself. If you want, I can do it next Monday or next Wednesday, if you feel that it's better that I do it, but I really encourage you to do it by yourself. Which will tell you that this phi function has the following two properties. One is that phi of P, G, is phi of P. Insist of putting the phi of G. And the second is that phi of G gamma is alpha gamma star phi of G. Okay? And now is where I really start coming back to the very original action of alpha on the space X. Okay? And this is true due to the identification I do when I go from G times X into G times X mod gamma. So this identification appears here. Okay? And that's why this is not really phi of G, it's alpha gamma star phi of G. And this is the way you act. So the gamma acts by homeomorphisms on the space X, so that's how you act on the probability measures of these omes. Now this allows me to and I'm still calling it just phi, a map from G mod P into probabilities of X. It's a Borel measurable map. And actually, since I defined Q there, I could even upgrade this not just for P in P. I will have this even for every P in Q because of the invariance. So this guy actually, I have it for every P in Q, just coming from the invariance, the Q invariance of mu. And hence, actually, I will have it from Q, but I rather will stop here for the P, and the Q will appear later. So I have this phi function, which is Borel measurable, and I have the natural action of gamma here, okay, which is this action multiplying by gamma, and I have the natural action induced by alpha here, which is this business here. And this equation plus this equation is telling me that this phi is a conjugancy between this action and this action. So this means that this is a factor, a measurable factor of this action. And that's how we are starting to relate these guys, these boundary guys, to the action of alpha. And this phi I'm writing here is this Furstenberg construction. Okay, so 3:30. Okay, it's actually very late. Okay, so on Monday I will recap a little bit of this so that we remember what is this function phi, and I will state Margulis Factor Theorem, which will tell me how this guy, how this phi, and how this guy actually look like. And once I have stated it, the proof of normal subgroup theorem will be almost finished in a second. And then we will still have to prove the factor theorem, okay? Which now will be a very dynamical statement. Okay, good. Thank you. See ya.